Okay, so today we're going to look at the chain rule, and we're going to look at finding the derivative of transcendental functions. But before we can find the derivative of a chain rule, first we have to look at some new derivatives we need to learn, and derivatives of trig function, exponential functions, and logarithms. Once you learn these, we can use the chain rule to find the derivative of composite functions. All right, and so once we can find the derivative of composite functions, and the reason why we do the trigonometric functions, exponential logarithms at this time is because they're usually use the chain rule in order to evaluate these. So let's just start with the derivative of trigonometric functions. So we're going to find the derivative with respect to x of sine of x, and it is cosine of x. Then the derivative with respect to x cosine of x is negative sine of x, and the derivative with respect to x of tangent of x is secant squared x. And the derivative with respect to x of secant x, well, that is kind of unique. It's secant x tangent x. And the derivative with respect to x of cosecant x is negative cosecant x cotangent x. And derivative with respect to cotangent x is cosecant squared of x. Now, these are pretty cool. You can look at how these come about by using our definition of derivative to figure it out. But for now, you can just memorize the formulas if you want to. But notice that all the trig functions that start with c, their derivatives are negative, and they're the only ones that are negative. So that's kind of cool that that pattern happens. They also kind of come in pairs. Notice that the derivative of sine is cosine, the derivative of cosine is sine. That's closely related. And the derivative of tangent is secant squared, it's only square one, except for the derivative of cotangent, which is also the square term, is negative cosecant squared of x. And secant x is itself times tangent of x, and cosecant of x is negative itself times cotangent of x. So they're closely related to each other. So if you kind of remember in pairs, it makes it easier to do. All right, so what we're going to do is we're going to find the derivative with respect to x of tangent x secant x. Sine of x. Okay, so we've got to use the product rule here. So the first times the derivative of the second, derivative of sine x is cosine x, plus our second term, copy down, times by derivative of the second term, and derivative of tangent is secant squared x. Now, that is your derivative, but what we need to do is we need to do some simplifying. In order to simplify trigonometric functions, you have to remember some of those properties you learned in trig class last semester. Well, we know that tangent is same as sine over cosine. And secant squared x is same as 1 over cosine x, but writing that is not going to let me cancel anything else. It's not going to help me, so I'm going to keep it without making a fraction if I can. And so I would simplify this down to sine of x plus sine of x times secant squared x. Next, we're going to look at finding the derivative of logarithmic terms. And these are log functions. So we're going to start with just the first basic rule, and that's the derivative of log base a of x. And it is 1 over the natural log of a, whatever your base is, times by the inside, which is x. Often you'll usually see, because it's easier to write it, we write the x term first. So in most books you'll see it as 1 over x natural log of a. Now, to find the derivative with respect to x of the natural log of x, just remember the natural log is equal to log base e of x. And so that was how we define the natural log when you're in algebra class. So this would be 1 over x natural log of e, but remember the natural log of e is equal to 1. So this would simplify down to just 1 over x. So just remember the natural log of x is equal to 1 over x. The derivative of the natural log of x is 1 over x. Now let's look at exponential functions, the inverse of logarithms. So the derivative with respect to x of a to the x is a to the x times by the natural log of a. A to the x times by the natural log of its base. So it's very similar. Both of these are being times by the natural log of the base. And then the same thing for e to the x. It's e to the x times by the natural log of e, but we don't write that because natural log of e is 1, so e to the x is equal to e to the x. It's one of those few functions whose derivative graph is the same as its original function. The slope of all the tangent lines is the same as the original curve of the graph. It's kind of cool that that happens. All right, so let's look at example 2. We're going to differentiate this using our quotient rule. So low d high, and the derivative of 2 to the x, using our new formula, is 2 to the x times natural log of 2, minus high, which is 2 to the x, times d low, which is the 1 over x natural log of 3, all over low squared. Now this one's kind of messy, and there are different steps you can go to simplify it down. Depending on if it's a multiple choice question, you'll need to go until you meet one of the choices of the multiple choice. If it's a free response, all you got to do is pretty much distribute this, get rid of that parentheses on top, and multiply that to the x times that fraction. And I'll let you leave it like this in a compound fraction if you want. You will also often see that they'll factor out GCFs. You'll see us doing this quite a bit with the chain rule. So if you want to factor out your common term on the top there of the 2 to the x, that's legit. You can do that. You could also find common denominator to the fraction at the top, simplify it down, flip the bottom fraction and multiply, but I'm not going to require that. So either one of these two is completely legit simplifying for me. And you go into upper level calculus, you will have to see what your professors prefer. The stages of simplifying this differ by teacher to teacher. All right, so now that we've looked at our new differentiation rules for transcendental functions, let's look at the chain rule, because we're going to use these a lot with transcendental functions, but it also happens in any function where you have a compositive function. You have a function inside of a function. So this is used quite a bit in calculus because we have a lot of composite functions that we work with in real life. And so this is going to be a very powerful rule. You're going to use it quite a bit. So the official rule is if y is equal to f of u is a differential function of u, and u is equal to g of x is a differential function of x, then if I have the function y is equal to f of g of x, so g of x is my inside function, so I have a function inside of another function, and it's differentiable in front of x, I could find the derivative of y with respect to x by taking the derivative of y with respect to u and times it by the derivative of u with respect to x. We'll call this version 1, this technique. Or you can look at the function notation and say, okay, the derivative with respect to x of f of g of x is equal to f prime of g of x times g of x. And we'll call this version 2. They don't have official names, but just for my reference as I'm working through the notes. Now I'm going to work through the next two examples, example 3 and 4, using, for example 3, I'm going to use version 1, example 4, I'm going to use version 2. And so you can see the two techniques, and you can pick which technique makes most sense to you. And whichever one makes sense for you, you can work your trig functions, your chain rule functions that way, derivative problems that way. So you pick and choose which way after I teach you the two. Whichever makes most sense. So with the first version, first thing you got to do is identify your inside function. So 5x minus 3 is my inside function. So I'm going to call that u. I'm going to let u equal 5x minus 3. Then I'm going to find the derivative of just that inside function, the u. So we'll label that du dx is equal to 5. Then I'm going to rewrite my original function, replacing the inside with the new variable, the u variable. So I get y is equal to u to the 4th. Now I'm going to take the derivative of y with respect to just that u variable, that new equation I have here. So dy du is equal to 4u cubed. And then I'm going to use that first version definition of the chain rule. Remember, it said that dy dx is equal to the derivative of y with respect to u times by the derivative of u with respect to x. So what I'm going to do is I'm replace the dy du with what it is equal to. And we found it to equal 4u cubed. So I have 4u cubed times by, and I'm going to replace the du dx with what we found it equal to, which was 5. And then I'm going to multiply these together, and I get 20u cubed. Now don't stop here. The original problem was in terms of x, so your final answer has to be in terms of x. So you got to go back to your original variable. All you do is replace that u with what you defined it to equal to. So I have 20 times 5x minus 3 cubed, and that would be my answer. Okay, I'm going to do the same thing for example B here, where we have y is equal to sine cubed of x. But remember, before we differentiate that, sine cubed of x is the same as sine of x quantity cubed. So my inside function is actually sine of x. So I'm going to make that my u. So u is equal to sine of x. So derivative of u with respect to x, using those new trigonometric derivatives we just learned, is cosine of x. So I'm going to rewrite u in terms of, rewrite y in terms of u. And I'm going to find the derivative of y with respect to u, which would be 3u squared. And then I'm going to use my definition of my derivative, which is dy dx is equal to the derivative of y with respect to u times my derivative u with respect to x. And so that would be 3u squared times cosine of x. And then I cannot leave it with the variable n, so I need to replace that u with what we found it equal to, which is sine of x. And then remember, trig functions, we don't leave it with the parentheses here, so we'd simplify this down to 3 sine squared of x cosine of x. Okay, the last example, chose this one because it's very similar for the other one. I want to make sure you know the difference between b, which is y sine cubed of x, and c, which is y sine x cubed, because this time my inside function is the x cubed. It's inside the trig function. So derivative of u with respect to x is going to be 3x squared. And so y is equal to u, sine of u. And so derivative of y with respect to u is cosine of u. And so using my rule again, derivative of y with respect to x is going to be my derivative of y with respect to u, which we found to be cosine of u, times by my derivative of u with respect to x, which is 3x squared. And then traditionally we write our polynomial before the trig function. So we would rewrite that. Don't forget to substitute in place of u what we found it equal to, which is x cubed. So my answer to this one is 3x squared cosine of x cubed. Now that is version 1. Now I'm going to work the next 3, or problem 4, using version 2's technique. Basically, we're going to skip the step where you do the u substitution. We kind of do it in our head, kind of in a way. And so you still need to identify that. So here my function y is equal to this polynomial raised to the 12th power. So what you're going to do is you're just going to take that inside and think of it as just blah, just our term. And so here I have something raised to the 12th power. So we're going to use our power rule, and that's going to be 12 times that something, which is this polynomial, raised to the 11th power. And then we're going to times that by the derivative of the highlighted part, the inside. So the derivative of that polynomial inside is going to be 6x squared plus 6x minus 4. And then we're just going to kind of put these, just kind of write the terms close together. Now I'm not going to distribute the 12 to each of those terms in the parentheses. You can if you want to, but it is not required. And so I'm just cleaning it up a little bit. And this would be the answer to A, for A, using the version 2 technique. Let me give myself a little bit more room. Okay, so I'm going to do the same thing with b here, but before I try to find the derivative, just remember that the square root of x, the square root of something, is the same as raising something to the 1/2 power. So my inside is that 4x squared plus 3. So when I take my derivative of y with respect to x, I'm going to take 1/2, that something, that highlighted part, and then 1/2 minus 1, decrease my power by 1. It gives us negative 1/2. And now I'm going to times that by my derivative of the inside. And then just clean this up. So half of 8x will simplify down to 4x. And then notice my original problem does not have a fraction power, and it does not have a negative power, so my final answer can't have that. So I'm going to bring that whole term 4x squared plus 3 to the denominator. And bringing it down to the denominator makes it a positive power. And then I'm going to rewrite it underneath the square root to get back to our original square root instead of fraction power. So that's how you'd write the answer to this one. Okay, C, I'm going to do with version 2, but this time notice that my inside is a quotient, so I'm going to have to actually use the quotient rule in addition with the chain rule. So we don't often use the other trig rules with us when we're doing these chain rule. So I notice my inside function for C is that 5x squared plus the 3x squared, 5x squared divided by 3x squared plus 2. And so the derivative of y with respect to x is going to be, I have something cubed, so I'm going to use my power rule first, and that's going to become 3 in that inside highlighted part, raised to the 2nd power, times by the derivative of the inside. Now, in order to find the derivative of the inside, this is a quotient, so I got to use my quotient rule. So I got to take my low d high minus high d low all over low squared, low. Okay, now this is the first one. I'm going to have to do some significantly simplifying down to work with it. So I'm going to start by just simply remembering that if I have a quotient, a fraction squared, it's the same as squaring the top and squaring the bottom. So I'm going to distribute that square to the numerator of this fraction and to the denominator. And for my quotient term over here, my quotient rule, I'm just going to simplify this top by distributing the 10x. And 10x times 3, oh, wait, something's wrong. There we go. That should have been x cubed plus 20x squared minus 30x cubed all over our denominator. Okay. Now, 5x squared is 25x to the fourth times by 3, which will give us 75x to the fourth as our new numerator of this first term. And I got the bottom down to 20x squared over that 3x squared plus 2 quantity squared. And now I'm going to multiply these two fractions together. So that gave me 1500 x to the 6 and 3x squared plus 2 to the 4th power. All right, last one. So my inside function is tangent of x plus 10. So power comes in the front, copy down my inside, decrease the power by 1, times by the derivative of the inside, which will be secant squared of x plus 0, which I'll just write secant squared x. And then clean it up a little bit. Only thing I do is put the secant squared x and the 21 together. So I got 21 times secant squared x times my tangent of x plus 10 raised to the 20th power. And that's it. Now, notice I've only used the chain rule once, but the neat thing about the chain rule is that you can use it multiple times. You can embed functions inside of functions inside of functions, and you just keep adding links to your chain. So when we differentiate a composite of 3 or more functions by applying the chain rule repeatedly, we just keep adding links in the chain. This is most easily seen with version 2 of the chain rule. You can do it with version 1 as well. You have to really watch your steps. So notice my most inside function here is cosine of x, which is inside my e to the e function, e to the x function, e to the u function. But e to the u, that e to e is inside my sine function. So I'm going to start by taking the derivative of my most outside function, derivative of cosine. Derivative of sine is cosine of the inside, times by the derivative of the inside. Well, start with the outer part of it, which is the e, the exponential. And remember, the derivative of an exponential is simply it's itself. Then I got to times it by its inside function, and the derivative of cosine of x is negative sine of x. And that's adding 3 links of to our chain rule here. Let's clean it up a little bit. And we get negative sine of x, e to the cosine of x, times cosine of e to the cosine of x. And that would be our answer. The main thing about cleaning up here is you needed to move that -1 to the front. And the order you write the other terms really don't matter. There's no certain rule for that. All right, that's it for today. We'll continue with different chain rule on our next video and learn a little bit more.